So then we want to look at how atorvastatin was developed. Originally, people that were looking into the cholesterol pathway were looking into this one compound that's called tryptophanol. So the only problem with this one was that it was inhibiting late in the pathway, and this ended up having disastrous side effects, including cataracts, other cutaneous effects. It was just not a great compound, and it was pulled pretty much immediately once it hit the market. And what was happening was it was inhibiting it fine, but then the original substrates for that enzyme, they were just building up and causing the side effects. And so this raised doubt in a lot of people's mind. Could you safely inhibit the cholesterol pathway? And so people needed to find a different way to do that. So next, people were just looking at some fungi and seeing what kinds of compounds they could come up with. And they actually found two separate ones that had the activity that they were looking for. We have mevestatin and lovastatin. So we have mevestatin up top and lovastatin over here. And we can see that the only difference is this one methyl group here. Now, mevestatin was discovered first, so it was the first statin that was discovered, but it was not the first one that was approved and put on the general market for people to purchase, because that was the lovastatin. They had pretty low IC50 values in the submicromolar ranges, and as isolated fungal metabolites, they were already pretty known to be fairly safe. However, they decided to try to simplify it. So they figured out that the naphthalene portion of it, right over here, that part of the molecule wasn't necessary for binding. And so they simplified the ring structure. And what they came up with was this parole template here. And so they did some more tests, and they were able to conclude that the 5 and 2 substituents on either side of here could be no farther than 10 angstrom apart, and that substituent 2 could be no longer than 5.9 angstrom, while substituent 5 could be no longer than 3.3 angstrom. And then after that, they boiled it down even further and saw what was absolutely necessary for binding was the HMG moiety here, and a hydrophobic region situated in the correct spatial arrangement. They found that they went through a lot of different functional groups that they put here and here, and they eventually found these two groups to have the best out of a tri-substituted parole template. And so we have here our fluorophenyl group, which gives it the extra binding interaction there, and then the isopropyl group with its hydrophobic region. And it turns out that the isopropyl group fits right into a shallow hydrophobic pocket, and so that gives it its hydrophobic interactions. And this particular compound had an IC50 of 0.4 micromolar, so not quite as good as the fungal metabolites that they were finding, but they were able to get down to a pretty good number. And so that gave them hope that they were going in the right direction with this. So next, what they did was they developed some new chemistry techniques, and they were able to completely substitute every part of the parole ring. And so they were able to put on this amide group with the phenyl ring coming off, and then just the phenyl ring here. And this allowed it to have more binding interactions. And this eventually became atorvastatin. And it's taken orally once per day, 10 to 8 milligrams per dose. And it turns out that this is a chiral compound, and they ended up finding that the RR stereoisomer of this compound was the one that had the vast majority of the bioactivity for this compound. And so they decided to market the drug as the pure stereoisomer instead of a racemate, so that the consumers didn't have to metabolize half a pill when the other half was basically useless in terms of giving activity that you want. And it has a very low IC50, and so that was great news for them. So here we have our different types of statins. You may remember seeing the differences between these. So these are like the first ones that we were looking at, the ones that were fungal metabolites. They weren't synthetic, they were organically made. And so type 1 and type 2 both have the HMG moiety here and here, but they definitely differ in these parts. And so you can have the butyryl group here, while you have the fluorophenyl group here. And then you have the decalin, naphthalene group here, and instead you could have a pyrimidinol group, or you could have a pyrrole group like you have for atorvastatin, and then you have the isopropyl group here. And so when looking to make new types of statins, most people go right to the type 2 statins. And so we can see here in the kinds of statins that were made after atorvastatin was made, we have rosuvastatin, which brand name Crestor, and we have cerevastatin. So cerevastatin actually didn't do so well. It was looking like a pretty good candidate, like it has pretty good IC50 values here, but then it went on the market and people started coming down and dying of rhabdomyolysis. And that is where your skeletal muscles start breaking down, and the myoglobin in your muscles are really bad for your kidneys to try to filter, and this can lead to kidney failure if it's not caught in time. And so cerevastatin had a fairly short run as a drug that was marketed to the general public. So that one didn't work out very well. But we have rosuvastatin here. And rosuvastatin actually was an improvement on atorvastatin. So like atorvastatin, rosuvastatin has an additional binding site that none of the other statins has. But except instead of the carbonyl group that's binding, it's the sulfone oxygen atoms here, and they bind with the serine residue. Unique completely to rosuvastatin, though, it has an additional polar interaction between the sulfone group and the arginine 568 side chain. And so that improves the IC50 value from where it was around 7 to 10-ish for atorvastatin. It's now 5 for rosuvastatin. And so it has better binding. And so that is where we'll leave that.